So the next piece mathematically that comes after sequences is series. So the difference between a sequence and a series is that the sequence is a list of terms, okay, like we talked about in 9.1. So this notation right here is just the set of all of the terms a sub n, and this notation is kind of like the evaluation bar from n equals 1 to infinity, okay? So if we have a sequence, it's just a list of terms. When we start adding the terms in the sequence together, then we end up with a series. So if we're not adding up all of the terms in the sequence, then we get what's called a partial sum, okay? And we use this capital S notation to represent a partial sum. So capital S sub 1 is the same thing as just the first term in the sequence. Capital S sub 2 is the first term plus a second. S3 is A1 plus A2 plus A3. I think you kind of get the picture here. S sub n is A1 plus A2 all the way to the nth term. Or using the summation notation here, we can write this as the sum from 1 to n of A sub I. Okay? This right here is called the nth partial sum. Oops. Okay? S sub n is called the nth partial sum. All right. Now, all of these partial sums form another sequence. So this right here, this is another sequence notation here where we're saying the set of the partial sums. So this would be, the first one would be S sub 1 and then comma S sub 2, comma S sub 3. And this is a list of all n terms. And we can go from n equals 1 to infinity. Okay. All right, so for this example, we have this summation notation, and we are going to compute the partial sums S sub 2 and S sub 6. So S sub 2 means I want the first term plus the second term. Now here I do need to pay attention to what the index starts at. It tells me that the index starts at 1. If this was a 0, then the first number I would plug in would be a 0. All right, so plugging in 1, I get -1 to the first times 1 to the negative first, which actually we could write this as -1 to the k over k if we wanted, same thing. Okay, so that's going to be -1 over 1, or just -1, plus the second term would be at k equals 2. -1 squared is positive, and then over 2, so that's +1 over 2, and then we can add those together and we get -1/2. So the second partial sum is -1/2. All right, and then for the sixth partial sum, we already know the first two terms add up to -1/2. Now we need to add the third, fourth, fifth, sixth terms to get the sixth partial sum. Okay, so our next term is going to be at k equals 3, so that's -1 to the third, so this is going to be negative, and then 1 over 3, plus -1 to the fourth over 4, so +1/4. Okay, plus -1 to the fifth, which is -1 over 5, and then -1 to the sixth is +1 over 6. So again, I got this one I got because I already knew the sum of the first two terms, but then I'm adding the third, fourth, fifth, and sixth terms together just from plugging those values in for k. All right, and this adds up to -37 over 60. Feel free to get a common denominator and add that on your own if you don't believe me. Okay. Some more terms here. An infinite series is defined as the limit as n approaches infinity of the nth partial sum, okay? Or in other words, the limit as n approaches infinity of, and then this is with the summation notation. And then so these two things are the same. This one is written with proper limit notation. This one is not, but I will tell you that you'll see this because, as you are aware, sometimes we get tired of writing out limit on everything, okay? So sometimes it is okay to get a little bit lazy there, but yeah, so these two notations are the same. As long as this limit exists, okay, then we can find the infinite sum, okay? Also, sometimes, just to be a little bit even lazier, this can sometimes be written as just the sum of a sub I. This is only going to apply when we're doing a lot of the same thing. So you might see this every once in a while, but this just means the infinite sum. Okay, if there's no limits on here, we always go from 1 to infinity. Okay, so the nth partial sum, this should be a capital S, just a typo there. So the nth partial sum, S sub n, converges. Okay, we talked about sequences converging. Now we're talking about the series, okay, the sum converging if the limit does exist. Okay, so if S exists, okay, in other words, it's a number, okay, not does not exist or infinity or negative infinity, but an actual real number. If that limit exists, then we say that the nth partial sum converges, okay? Otherwise, we say that it diverges. Okay, so, and we're going to do a lot of testing to see whether series converge or diverge. All right, so if that's still a little confusing, just sit tight and we'll get to a bunch of them. Okay, so here I have a series and I'm looking for the sum from 1 to infinity, so infinite sum of 1 over k squared plus 5k plus 6. This is one where we can approach this a couple of ways. One thing we could do is we could look for one of those series formulas, like the linear, constant, quadratic, etc. However, you're not really going to find those very often because those tend to not converge, okay? Because we'd be approaching infinity, and raising something to an infinite power will tend to continue to get bigger and bigger. So we need another approach to this type of problem. For this one, k squared plus 5k plus 6, you might recognize that as a trinomial that factors. Okay, so I'm going to write this in its factored form. Whoops. As the sum, oops, k not I, from 1 to infinity of 1 over k plus 2 times k plus 3. Okay, the reason I do this is because I'm going to start writing out some terms. Okay, and if I can break this down, hopefully I will see a pattern, because otherwise I'm going to have to add an infinite number of terms and we'll be stuck forever. So from here, you might be saying, hey, I know how to split this into two fractions, because yes, you did in fact learn partial fraction decomposition. I'm going to go ahead and give this one to you. This is the same thing as the sum from 1 to infinity of 1 over k plus 2 minus 1 over k plus 3. Now, this type of a sequence is one that will occasionally occur. When it does, you need to recognize it. It's something where we have two fractions where the index variable is in the denominators, and they're usually going to be pretty close to each other, like k plus 2, k plus 3. Not necessarily exactly sequential like that, but pretty common, okay, that they are going to be subtracted as well. And this is something that is called a collapsing or a telescoping series, just depending on what book you're looking at. Okay, a collapsing or a telescoping series. The way that we evaluate this is we start writing out terms and we want to look for a pattern. Okay, so if I start plugging in values for k, if I plug in 1, I get 1 over 3 minus 1 over 4, so that's my first term, plus, and then the next term would be when k equals 2, I'd have 1 over 4 minus 1 over 5. Already we can see something's going to cancel, plus 1 over 5 minus 1 over 6, okay, plus 1 over 6 minus 1 over 7. Okay, so we see this pattern where the second half of each term is canceling with the first half of the next term. Okay, so that doesn't mean that we can find the sum yet, but that does mean that we can observe a pattern. So now we need to look and say what's happening at the other end at infinity. Okay, so to do this, now pay attention to this notation, please. When we are adding an infinite number of terms, we put plus, dot, 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 plus, and then we put the end terms after this. But this is the correct notation for continue in this fashion all the way up until, and then whatever goes behind it. Okay, so please use that notation appropriately for this type of situation. Okay, so let's do the next to last turn. Okay, so it's not written, but again, we can assume that we have a limit as n approaches infinity here, and then we'll call that an n. So then my nth term would be the very last term, and then we say limit as n approaches infinity. Okay, I'm going to start with the term right before that. So the term right before the last one is going to be the n minus 1th term. Okay, again, last term is the nth term, so the term right before that is going to be a sub n minus 1. So a sub n minus 1 would be 1 over, so I'm plugging in n minus 1 here. So n minus 1 plus 2 is just n plus 1 minus 1 over n plus 2, okay? And then the last, so this is the next to last term, and then the very last term is going to be 1 over n plus 2 minus 1 over n plus 3. Okay, why did I do this? Well, I know that this 1/7 will cancel out with something in here, which will cancel out, et cetera, et cetera. So whatever's right before this, the second half of that term will cancel out with this. These two cancel out, and then I can see that this term and the 1/3 are the only things that don't have an opposite pair to cancel out with. So this is actually the limit as n approaches infinity of 1/3 minus 1 over n plus 3. And then this we can evaluate, okay? That's just 1/3 minus 0, which is 1/3. All right, so the infinite sum of this series is 1/3. Even though there's an infinite number of terms, the sum of all of those terms approaches 1/3, okay? Now, something I want to highlight here that's a little bit different. The nth term does approach 0, okay? If I just said, as n approaches infinity, what's the nth term here? 1 over n squared plus 5n plus 6. That term is going to approach 0, but the sum does not approach 0, okay? So let me write that down. The nth term approaches 0, but the sum of the nth term approaches 1/3. Okay, so this is the difference between the sequence, what does the sequence approach, and what does the series approach. Okay, speaking of nth terms, let's look at the nth term divergence test. So this is the very first thing that you should always check when you are trying to decide, does a series converge or diverge? Now, something important here is this is only a test for divergence. In other words, it cannot conclude that a series converges. It can only conclude if a series diverges, okay? If the nth term does not approach 0, then that means the infinite sum has to diverge, okay? So let me say that again. If the last term does not approach 0, well, that means that if we continue to add things and the value that we're adding isn't getting closer and closer and closer to 0, we can't approach a finite sum. Okay, so therefore the series has to diverge. All right, now I'm stressing this a lot because it's going to be a very easy thing to mistake. It is not a biconditional. In other words, we cannot say the converse of this, where we can't say if a sub n approaches 0, then, so I did the converse of, or I'm sorry, this is the inverse of the negation of this term or statement and negation of this statement. So if a sub n approaches 0, then the series does not diverge, or in other words, converges. This would be the inverse. If this is if the biconditional is true, then this would be true. This is wrong. Okay? Wrong. Nope, does not work. Okay? Does not work. All right. Again, I'm making a big deal of that because some of you are still going to do that wrong. You start by checking, does the last term approach 0? But if the answer is yes, then we cannot draw a conclusion, okay? So if a sub n approaches 0, then this test is inconclusive and we need to try something else. Let's make an even bigger deal out of it. Let's highlight it in yellow. Okay. If the nth term approaches 0, then the test is inconclusive. All right, hopefully I made a big enough deal there. We are, let's see, well, yeah, I'll go ahead and do this one. So show that the series cosine of 1/2 plus cosine 1/3, cosine 1/4, etc. diverges, okay? Well, as a series, we could write that as the sum from, the sum from, and I'm going to use I, so the sum from 1 to n, and then limit as n approaches infinity of cosine of 1 over I. This would be our summation notation for this series, okay? So because the nth term, so cosine of 1 over n at infinity would be equal to cosine of, and then 1 over n approaches 0, cosine of 0 is 1, which is not equal to 0, then that means we can conclude three dots in a triangle, remember, means therefore. Therefore, the series diverges. Okay? All right, one more thing here. A geometric series with a common ratio. So we talked briefly about what the geometric sequence looks like. So a geometric series is just same form, but then adding all those terms together. If this is satisfied, remember, if the absolute value is less than of the ratio is less than 1, then that means it does the sequence does converge. If this condition is met, the series also converges, and this is one where we actually can find what it converges to. So really, the telescoping series and the geometric series are the two that it's easiest to determine what the series converges to. Not just yes or no, does it converge, but what does it converge to, okay? And the formula for that is a over 1 minus r. You might remember this from geometry, the infinite sum, a sub 1 over 1 minus the ratio. Okay, so you've seen this formula before. One thing to pay attention to is knowing is what your first term is. So in this case, because I have a k minus 1 right here, and the first term starts at k equals 1, then this would be r to the 0, meaning your first term is just what's right here. Okay, if this was r to the k, then the first term, in other words, the numerator would actually be a times r. So when we get to some examples, when we do these in class, I'll show you what I mean by that. Okay? And harmonic series we briefly mentioned already, but I'm going to stop here and we'll pick up with that in class.